Uh, Hello everyone, welcome to all of you. So in the next couple of minutes we'll be learning about this carrier transport phenomenon, as the title says on top. So we'll be learning the carriers, basically the electrons and holes, how they conduct the electricity in a semiconductor. Okay, so let's begin. Let's start my whiteboard. Okay. So in a solid, or rather in a semiconductor, the charge carriers, the electrons and holes, they basically move in two different phenomenon, right? One is your drift and another is diffusion, right? Now the carrier drifts because of the influence of electric field, and they diffuse when there is a concentration gradient. So first let's consider the carrier drift phenomenon. Okay, let's consider drift. Okay, so let's take on n-type semiconductor material. So we have a n-type semiconductor material where our majority of charge carriers are electrons, right? Now the electrons which are there in the conduction band, they are basically free, so we can consider them as a free particle, and we can estimate their thermal equilibrium energy by using theorem of equipartition, right? So it says that the energy per degrees of freedom is half kT, right? So energy per degrees of freedom is equivalent to half kT. Now as we know that electrons, the conduction band, they are free particles, so they have basically three dimensions because they can move all the three direction in the semiconductor material. So the kinetic energy of an electron in the conduction band, it's equivalent to, so kinetic energy is nothing but half mv square, as we have studied. So half mn into vth square, its equivalent to will be 3 different degrees of freedom, so 3 by 2 kT, right? Where mn is the effective mass of electron, vth is the average thermal velocity of electron, and these are the constant, and this is the temperature at which we are measuring in Kelvin. This is Boltzmann constant, as we know already. Okay, now if you put all these values, because see K is constant, T if you put at room temperature, so room temperature T will be like 300 Kelvin, right? So if you put all these three parameters, Mn effective mass of electron for a silicon, if you put, then the Vth, if you calculate, it will come around 10 to the power 7 centimeter per second. Okay, so this is for silicon or even gallium arsenide, they comes in this range. Now how fast is this speed? If you want to feel it, so you can consider a flight like the aeroplane, right? Aeroplane, the domestic or international for public uses, the velocity average speed is around 750 to 950 in this range, 950 kilometer per hour in this range. So if you convert this into centimeter per second, as we put it here, so it will come around roughly 2.8 into 10 to the power 4 centimeter per second. So you can see this order, right? The order of difference is of the order of 10 to the power 3. So the speed of electron at thermal equilibrium is 1000 times greater than of your any flight speed, so it's almost 1000 times higher. So you can imagine how fast it is, but we don't feel any any current when a semiconductor is sitting we don't see any current because of the random motion of electron, right? So they are moving randomly three-dimensionally. Now if you do a time average for a certain time, the net flow of electron at a particular area or cross section, if you say, it will be 0. So you don't see any current passing through a semiconductor when it is at thermal equilibrium, I mean when there is no electric field involved in it, right? Now okay, now if we apply an electric field, so what will happen? So if you apply an electric field, the carrier will start to drift, right? Now before going to the drift, let me move this page up. Okay, so before going to drift, there are two parameters, let's define them. So one is mean free path, okay, one is your mean free path. Mean free path, how do you define? It's the average distance between two successive collision. So if you take this, I mean if you calculate the average mean free path, it comes around 10 to the power minus 5 centimeter. Now the another parameter is mean free time. It's like average time between two successive collision. So you can calculate the mean free time, that is tau c is equivalent to 10 to the power minus 5 by the velocity you already got, right? So it was 10 to the minus 7 here, so minus 5, it will come around 10 to the power minus 12 seconds. So it's like 1 picosecond, right? So you can see the average, I mean the mean free time is very less, right? It's a 1 picosecond. And now when we apply an electric field, so what happens is basically any charged particle under electric field, it experiences Coulombic force, right? So the Coulombic force for an electron, it will be minus q into E, right? So what happens in a semiconductor when we apply electric field? So let me draw one semiconductor material here. Okay, let me just redraw it. Okay, so this is a semiconductor material. Now we are applying one electric field in this direction. So what will happen to the electrons? So we have electrons there, negatively charged, and we have also the holes. So the electron will experience a force opposite to the electric field, and the holes will experience Coulombic force according to the along the electric field direction, right? So for an electron, this is the force it experiences, right? Minus q into E. So in this electric, because of this change in because of this electric field or this they experience this force. Now it has basically two velocities, right? One, we already had this thermal velocity Vth. Now because of this force, electron will start to drift. So you will define another velocity called drift velocity, right? So for an electron we call it as Vn, and for an hole we call it as Vp. Okay, this is for hole. Fine. Now because of this drift velocity, so there is a change in momentum, right? So electron basically gains some momentum. So what will be the momentum of electron? It will be mn into Vn, right? So this is effective mass of electron, and this is your drift velocity. Now from where this energy comes or this momentum comes? This energy came because of the Coulombic force. So again we know the momentum is nothing but, we can write, right, momentum is equivalent to force into time, force multiplied by time. So this we can equate right now. So it will be, force is nothing, q into E, and time is, so okay, we will not put vectorically here, but we can put it vectorically. So this is Vn, so this is basically, okay, we can put vectorically as well. So into, so this is the force into time, so time is nothing but tau c, right? Now from this equation you can easily calculate Vn. So what will be the value of Vn? So in this equation, if you calculate Vn, will be minus q into tau c over Mn, right, and into electric field. So this you can put in bracket and electric field. So I am putting in bracket because this term, this within the bracket, within the parenthesis, it's basically a constant, right? Charge, electronic charge is constant. Tau c will be constant at a particular temperature for a particular material. Effective mass of electron also constant. So it's basically this constant, we call it as mobility, right? So we call it as mobility of electron, so mu n into E. So this term mu n, the mobility of electron, is q into tau c over Mn. Now similarly we can calculate, which is mu p equals to q into tau c over Mp. Now in this mu n, as you can see, this mu n, again, how does it vary? So mu n, you can see q is constant, Mn is constant, so it depends on again tau c. Tau c is nothing but your mean free time, right? Now comes different scattering mechanism. So the electrons or the carriers, they started moving, right? Now as they move around, they start experience this scattering effect, right, there in your lattice, right? So we have lattice, we have impurity. Lattice is nothing but your atoms, right? And then we have impurity atoms also sitting there. So there will be a lot of scattering phenomenon in this. While the electron moves, they will get scattered by lattice and also impurity, by the impurity atoms. Let me take a new one. Okay. Now coming to lattice scattering. So there are two scattering phenomenon. One is your lattice scattering. So let's talk about this lattice scattering. So as the temperature increases, the lattice vibration also increases, right? This is the thermal energy. So it disturbs the periodic potential, right? So the lattice scattering is dominant at higher temperature, because at higher temperature the atoms or the lattice vibration is more, so the electron, the probability of electron getting scattered will be more, so the lattice scattering basically increases. And theoretically, so if the scattering increases, the mobility will decrease, right, because tau c will decrease. So theoretically this mu L, I mean the mobility because of lattice scattering, it is proportional to t to the power minus 3/2. Okay. So the impurity scattering, when the carrier travels near, so this is for your lattice scattering. Now coming to impurity scattering. Impurity scattering. So impurity scattering, the source is because the presence of impurity atoms in the semiconductor. Now when a carrier travels near an impurity atom, the free path will be deflected, because impurities are most of the time they are ionized, and our carriers all are ion, again they are charged particle, so they will get deflected because of this Coulombic force. Now the probability of scattering depends on this concentration of impurity, right? If there are more number of impurity atoms, the scattering probability also increases. But one thing different here, like in lattice scattering, the scattering phenomenon increases as the temperature increases, but in impurity scattering it is other way around, because when the temperature increases the carrier moves faster. So because of thermal agitation they move faster, so they spend very less time near the impurity atoms, so the effect will be very less, or rather insignificant at very high temperature. So theoretically this mobility, because of this impurity scattering, this is proportional to T to the power 3 by 2 over Nt. What is Nt? Nt is your impurity concentration. Impurity concentration. Okay. So as you can see, the impurity concentration increases, your mobility decreases because scattering increases, and as the temperature increases your mobility increases because scattering decreases. So that's all about the mobility. Now coming to the probability of collision per unit time. So the probability of collision will be, because we know tau c is your mean. What was the tau c in the last? It's the mean free time, right? So if you take 1 by tau c, it's nothing but the probability of collision, right? Now the total probability of collision will be probability of collision because of your lattice, right, and also the probability of collision of impurity, and they are additive, right? Impurity. From here you can get 1 by mu equals to 1 by mu L plus 1 over mu I. It's because in the last equations we have seen that tau is proportional to mu. So overall mobility is related with this relation.